Hello, everyone. My name is Baron Schwartz, and I'm with Vivid Cortex. I'm the founder and CEO. And I'm going to get this webinar started in just a moment. All right, let's go ahead. So today we're going to be talking about the way that we use regression in Vivid Cortex to figure out things that can't be measured. Just a couple of logistics. If you're watching this, obviously you're on YouTube. If you're watching it live, then we've previously tried using the YouTube comments, but there seems to be enough of a delay and enough confusion that it's difficult. So instead, why don't you just tweet your questions to Vivid Cortex? I have Vivid Cortex's Twitter stream up on another screen, and I'm watching that real time. So there's going to be a little bit of a delay, something like 30 seconds or so, because you're seeing this video and audio at a slight delay anyway. But go ahead and tweet those questions to me, and I'll answer them as I see them. Okay, so I already mentioned who I am. I'm also the author of High Performance MySQL and a whole bunch of open source software for MySQL. And probably many of you have known me from the tools that I've written for MySQL and the performance analysis that I may have performed for some of you as a consultant when I was at Percona and so forth. There's a bunch of old friends I see on this webinar joining me, so welcome everyone. It's great to be here with you again. The motivation for this is how to figure out things like CPU time per query, and in fact any metric per query from either MySQL or the operating system, or indeed even other systems than the ones that MySQL is running on. And this little screenshot of part of our user interface shows the values that we want to fill in. And I'm actually going to just switch screens here real quickly to a live demo of how this works on Vivid Cortex's product. So I hope you can see that. Okay. The columns in the right-hand side of this user interface, the CPU time, InnoDB reads, and lock weights columns, are all computed through regression. The screen that you're looking at here is on a series of our production systems, and we're looking at top queries ranked by total time. That is the total time that all of these queries spend inside of the database server, and they're ranked from 1 through 8. And the blue bar at the left of the total time column represents the proportion of the query time consumed by that specific query. So for example, this first query, number 1, consumes 36% of the time in the server. And then we have a spark line that shows the variation of that query's time during the 3-hour time interval that we've selected here. And then we have these columns of CPU time, InnoDB reads, and lock weights. And those are just example columns. We can get any of the many thousands of metrics from the operating system or MySQL and plunk a column in there and see what that value comes out to. And in this case, you can see that these the CPU time that we're blaming on that query number 1 is 46 seconds of CPU time inside of MySQL. So that's how this began. I drew pretty much a napkin sketch one day of our top queries interface, and I drew in a column and I said, we ought to be able to figure out how much CPU time is being consumed by this query. And we ought to be able to figure that out for other things as well. We have CPU time in high resolution, we have the query time in high resolution. We should be able to figure out how much those things are related to each other. And I didn't know at that point exactly how that would work. I thought it might be correlation. I thought I actually wasn't thinking of regression. I thought that there might be some sort of heuristic or ad hoc way that we could do that. But regression was not something that I really had in my mind at that point. And this webinar is partially a story of that journey of discovery of regression, and partially of the variation of regression that we've ended up inventing in order to serve our unique needs here. So one of the questions that people often ask me when I say we use regression to figure out how much CPU time or other resources a system consumes in its queries, they often say, well, why don't you just measure that? Why don't you, IOs, like NODB reads, buffer reads, or those kinds of things. Why don't you just measure those things? And there's a few answers for that. One is oftentimes those things are not instrumented. And in fact, the majority of things are not instrumented at a per query level. There are global counters for lots of things in MySQL and in the operating system, but most of those things are not instrumented per query. Even if we were able to measure those things inside the server, or had access to those measurements inside the server, that would be a lot of data. It amounts to really high dimensional measurements on queries that there may be a very high cardinality of queries. Some of our customers only have a couple of 100 distinct types of queries, but some have many millions of distinct types of queries. So we're talking about a metrics explosion here. And that's not only less data for us to measure from customer systems and transmit across the network to our software as a service platform, but it's also a lot less overhead on customer systems. If we were measuring every possible thing of interest at a per query granularity, that would be an enormous amount of overhead on the server itself. Finally, well, not finally, there's two more points. It allows us more flexibility because it allows us to perform post hoc analysis on things that otherwise we would have to think about in advance and plan to capture that data in advance. In other words, we can capture data and we can do essentially what amounts to high dimensional analysis on it without ever having to decide in advance, we think this is something of interest for high dimensional analysis. Let's measure it in high dimensions. We can measure it in low dimensions and use regression to essentially disaggregate that and give us high dimensionality. And finally, in some cases, it's more accurate. And CPU time is a good example here. A lot of work that's performed in the server could not be blamed on a specific query or classes of queries because of timing issues. A lot of work for an insert, for example, happens well after the insert completes. And it's done in cost-sharing types of ways such that, let's say, multiple inserts perform a bunch of work that then gets deferred and combined and done lazily in the background. And that background work, by necessity, is detached from the foreground queries that caused it and cannot be blamed on a single query anymore. However, regression can help us to tease out the actual cost that those queries eventually impose on the system. So in order to explain exactly what we're doing here, I mean, this is a generic functionality, but it seems to help a lot to have really specific examples of what we're doing. The way that we measure queries and the operating system statistics that we're relating to those query classes is actually highly relevant. So let me switch back to our user interface in our tool and show you again what we're looking at here. So there are two kinds of things that we're relating together. One is the classes of queries, or you can think of them as types of queries or digests. And the other is the operating system statistics for the MySQL deep process. So let's switch back here. Each of the rows in this table represents a particular class of queries. So I've selected row number 4, and its details show up in the right-hand sidebar. And if I select Show Code, we can then see, let me resize this just a little bit. We can see the abstract form of that query with everything lowercase, white space collapsed, and literals replaced by question marks. So we digest these queries like this in order to group similar queries together. And this becomes the identifier of that class of queries. So what we're doing here when we measure this, this query's execution time, is we're watching for queries to enter the server, and we're timing that. We're looking at the network traffic, so we're timing when the query starts executing in the server. And then when that query completes, we stop the timer and measure the elapsed time. And this happens a lot. So there may be thousands or many thousands of queries per second for a given class of queries, and we're reducing that down to a single metric by once a second firing a timer in our code. And that timer measures the elapsed sum of all of the queries that have executed within this class. So for example, if 1,000 queries per second are coming through the server, and each of them takes a millisecond, At the end of the second, we're going to have counted 1,000 and we're going to have accumulated 1,000 milliseconds or 1 second. And so we're generating aggregate metrics once per second, and we do everything in 1 second resolution. And we're generating those aggregate metrics about each class of queries. So this spark line that you're seeing in the center of this user interface is generated from one of those aggregate statistics where we have that 1 second resolution data. So we're reducing lots and lots of queries down to, essentially you can think of it as a sampling technique, but when I say sampling, oftentimes it confuses people as to exactly what that means. We're measuring all of the queries, but then we're just taking these incremental measurements of what the running sum of those queries has added up to during the second. And then we're also capturing process data. So let's look at the top processes view over the last 3 hours as well. And on these servers that we're looking at, this group of servers being displayed all together, you can see the MySQLD process. And we measure various things about that, including the user CPU, the system CPU, and so forth and so on. And then we're capturing statistics about this and turning it into a metric in a fairly similar way. In this case, we're looking at the proc file system, which is the same thing that tools like Top and so forth look at. And so what this page represents here is basically a top with a timeline history on this server. So we're stitching those two metrics together, the user CPU and the elapsed query execution time for this class of queries. So hopefully that makes it clear what we're measuring and how we do it. Now, it turns out that there's a bunch of fairly standard classical statistics for taking an aggregate measurement like CPU per process and highly detailed metrics like elapsed query time per class of queries, and then relating the two of them together. So my co-founder and I spent a lot of time digging into this and seeing what exactly are the well-known techniques. I knew we wouldn't have to come up with something completely from scratch, because I knew that problems like this had been solved a lot before. For example, when trying to determine the efficiency of a particular medical treatment for a particular condition, and there are a lot of things that may bring some influence to bear on a patient's condition or a set of patients' conditions. I know there are statistical techniques that are used to try to correlate particular treatments with particular outcomes and try to figure out the statistical significance and relevance of the treatment and the outcomes. So I knew that there was a lot of related work, at least, even if nobody had done something exactly like this before. So the first thing that we wanted to do was look into the standard techniques. And the classical technique here is linear regression analysis. Again, this wasn't I was fairly ignorant of this at first. I'd heard of regression, and I knew of it as fitting a point to fitting a line through a set of points, but I didn't know what it did or what it meant. So I'm going to give you a quick primer on linear regression, and I'm going to relate it to this example that we've been using here. So in regression, you have a y variable, and you have one or a number of x variables or independent variables. And the y variable is the dependent variable, which means that the x variables essentially determine that y variable to some extent. And you end up with an equation that looks like y is determined by some constant, usually known as the intercept, plus the sum of a whole bunch of x variables times a coefficient. And you can think of those as a slope. And in our case, the CPU time is the y variable, because the queries are the x variables. And the sum of all of these queries times the coefficient of CPU per query plus a constant theoretically equals the total CPU time of the MySQLD process. This is usually shown in 2 dimensions with some points, and the technique that's used here to generate a line through those points is by minimizing the sum of squared errors. And here we've drawn a square between each point and the line, and the square's sides are the same as the distance between it and the line vertically. So you can see visually that the errors are being squared. And then you add together all of the areas of those squares, and that becomes the sum of squared errors. And the goal of regression is to minimize that sum of squared errors. Now, there are other types of regression analysis, but this is the most straightforward and most commonly used. This is what most people think about when they're thinking of a least squares fit to a set of points. This is in 2 dimensions, where we have one x variable and one y variable. And this generalizes to any number of dimensions. So we can only visualize it in a couple of dimensions before we kind of run out of our concept of space and time. But here's a visualization of this in 3 dimensions, where we have 2 x variables, x1 and x2, and we have the y variable going up, really in the z direction is the way most people would think of it here. And then what you're doing here, instead of fitting a line through some points, you're fitting a plane through these points. And you still have that intercept. That's the distance between where that plane touches the y-axis and the origin where all 3 of those lines come together. So you have one coefficient, I'm sorry, you have one intercept and you have multiple coefficients. There's a coefficient for each edge of that plane, for each dimension in that plane. In this case, you're going to have 2 coefficients, one for each x variable. And the multiple linear regression minimizes, again, the sum of squared errors, which the errors are the distance between the plane and the little red points. There's a bunch of variations on linear regression as well. There's all sorts of constraints that you can put on regression. So you can constrain, for example, that the slopes have to be positive or the intercept has to be 0. And you can do things like you can smooth and take samples out of your data. You can do step regression, where it's essentially an optimization problem. There's local regression, where you can do regression on little bits of your data, a little bit at a time, and then look at what the bigger picture starts to tell you overall. Logistic regression, where you're looking at variables that are either true or false. There's all kinds of optimization techniques and actually completely different ways to approach this, but most of the time you're essentially going after the same thing. You're going after developing some model. In this case, the model is a hyperplane in a hypercube, or an n-dimensional space, that minimizes the distance between what your model predicts and what your measurements observe. And we tried a bunch of these. There are packages for all of these kinds of things with varying levels of functionality. And we found a couple of problems with lots of them. In fact, we even tried some commercial software. Like there's commercial software that people use for financial market analysis and so forth. And some very advanced stuff, and talked to a lot of PhDs and experts in the fields of statistics and so forth. It was a really fun learning project, and it took a couple of months really of time, more or less dedicated by at least one person at a time. And we found a few problems with all of these approaches, where they didn't just quite satisfy our unique requirements. Many of them were extremely complex, and partially because they're designed for very general problems, whereas we have a fairly specific problem. Many of them are also very slow and costly, and even quadratic in some cases in the number of x variables. And we can have a lot of x variables. As I mentioned, we may have up to millions, tens of millions in some cases, of distinct types of queries that we can observe off of a system. So that becomes a combinatorial explosion that's very difficult computationally. A lot of them also are designed for getting partial results, so results only for the most significant contributors. And there are lots of cases where unphysical or strange things can happen because of particularities about the data that are highly correlated. For example, some of the x variables can be highly correlated. And we can see that, I believe, in this data. You can see that query number 4, query number 7, query number 2 have activities around the same times and similar shapes. And so what happens there is that they become, similar shapes is the same thing as saying that they're highly correlated, essentially. And highly correlated x variables become difficult for many of these algorithms to tell apart. So I'll switch back to my slides here. So here's an example of how this can happen. This slide shows a few of the metrics off the system. The first two pictures from the left are a couple of the query variables. So there's a user CPU time for a query on the left, and then a query in the middle, and then there's user CPU time for the MySQLD process. And this particular set of data, by the way, is available online. It's on our GitHub repository, and I have links to that and other resources at the end. So, and there's source code. You can reproduce my results and play around with it. So the thing to notice here is that if you kind of squint your eyes a little bit, the first query has a hump and then a dip, and then it comes back up again. And so does that last graph on the far right, where we have the server CPU time. It goes up, and then it goes down, and it starts to come back up again. So it looks like that first query and the server CPU time are somewhat related. Now, interestingly, the second query has almost a mirror image reflection. It goes down first, and then it comes back up and starts to decrease again. So it's kind of inversely correlated to the server CPU time. And this is one of those areas where standard multiple variable linear regression gives us a weird answer. If we do multiple variable linear regression on these things and then plot the scatter plots of the outcomes, it ends up looking like the first query versus, I'm sorry, I spoke wrongly. We haven't done regression yet. We're just plotting the one variable against the other. So on the left, we have the first query against the CPU time, and on the right, we have the second query against the CPU time. And you can see what I was saying, that the first query seems to be linear in an upwards direction. The second query seems to be linear-ish in a downwards direction. There seems to be a strong trend there. So one of these has a positive slope, and the other has a negative slope when you just plot them against each other on an XY plot. And this ends up being kind of sort of what regression kind of does to these. Regression is going to essentially fit the hyperplane such that each set of coefficients sort of normalizes as best as possible a line through the middle of these scatter plots. And you're going to have one of these scatter plots for every dimension that you're performing in your regression. And you'll essentially have a line that kind of goes through these. It's not exactly that. I'm simplifying a little bit, but it's pretty much what regression is going to do. And what we end up getting out of that when we do standard regression is we get an estimated coefficient for our first query that's positive. It's 1.895. And we get a pretty negative coefficient for the second one. And so that kind of matches what we were seeing on that picture. Now, this is only a partial result. There are hundreds and hundreds of rows in the output from R here. But this illustrates the partial result for those two classes of queries that I just showed you. And what this means is something is unphysical here. That negative coefficient has a whole lot of different mathematical interpretations, but one of them, and the most physical interpretation here, is that the more you run this query, the less CPU that the server is going to use. So it means that this query causes negative CPU usage in the server, and we know that's unphysical. So that turned out to be the case in a lot of the regression techniques that we were looking at. That, along with many of these other things like correlated X variables, fooling it in it, not knowing how to allocate the CPU usage or other outcome amongst them. And so we ended up getting results that only made sense in some cases, and that in other cases they just gave us an answer that a database administrator would look at and say, well, that's clearly bogus. You know, queries don't cause the CPU to run backwards. So we kind of had to stop after we had exhausted all of the resources and literature and R packages and so forth that were available to us, and try and design something of our own that would be constrained to meet our requirements. And our requirements are fairly specialized. It's not a general case. There's actually some very particular things about our data that mean that we could perhaps design something simpler and more tailored for our use case. There's a couple of requirements in this. One is that it needs to be memory and CPU efficient for large data sets. And even with a moderately sized data set, we were having trouble with some of the standard techniques. Some of them we never even let run to completion because it looked like it was just going to be the heat death of the sun before that they would complete. We also need to get full results. Many of the techniques that we looked at, sort of a best practice is to only look at the top 3, or sometimes people will say up to 10, but almost nobody says many more than that, contributors. And I wanted to figure out, even if we have this one query that's a really minority contributor, how much CPU is it really using? I didn't want to say, well, this one's such a minority, we're just going to exclude it from the calculation. So I wanted to get full results for even millions of classes of queries. I didn't want to have to pre-compute anything. I wanted to just gather this data and then do the computation on demand. Ad hoc analysis is so much more flexible than analysis that you have to plan for up front. I wanted to get reasonable accuracy, and I wanted it to be simple and physically realistic so that we didn't get things like negative coefficients. And I also wanted simplicity so that it would be something reasonable for us to actually implement. There were a few insights that I just had some intuition about this. And it said, Baron, there's a simpler way to do this, and we should really look into this. First of all, non-negative slopes should be disallowed. Secondly, we basically have identical dimensions in a lot of cases. So we'll have, we'll regress the count of queries against the count of InnoDB buffer pool reads, or the count of queries against the count of rows sorted, or something like that. Or we'll regress the time of queries against the time of CPU. So we have variables that are fairly similar and have identical dimensions. Also, the X variables are generally independent. The X variables generally don't cause one another. And a lot of the complexity from standard regression comes from having to compute the cross product of a lot of correlation coefficients. So you not only have to compute the cross product of all of the X variables against the Y variable, but also of all of the pairs of X variables, which grows rapidly with the number of X variables. All of the variables in our case are significant. It's clearly the case that if a query runs, it is consuming some CPU. And I already said this, but the variables are roughly similar in size. We don't have variables where we have tiny, tiny effects, and variables that we have enormous effects. And then just for fun, because I was illustrating the requirements with this the spacecraft diagram, I said we don't need ion cannons. So I actually started out calling this cowbell regression. And this goes back to the Saturday Night Live skit where the group of people is playing some music and Christopher Walken says, it needs more cowbell. And I had a feeling that if we started looking at some real data sets and just kind of follow where the data takes us and look at, try some regression, try something maybe heuristic and see where it needs a little bit of this or that, a little bit more cowbell. What I ended up doing was discovering essentially that we could go back to regression with a variation. So this is how it works. So we begin with all of our X variables, and we stack them on top of each other. We sum them up and we stack them on top of each other for a particular slice of our data. We're going to iterate over every slice of our data in those spark lines from left to right. So we have a time series metric over some period of time, and we're going to take all of the samples in that time series and iterate over it. And each of those samples, for a slice of that, we call a set of X variables and we pile them on top of each other. And then we get the corresponding sample of the server's CPU usage, and we call that our Y variable. And then we figure out what the ratio between those X variables and that Y variable is. And here it's something like 1.2 or so forth. If you multiply the colory box on the left by 1.2, it will approximately get as big as the box in the middle. And then we do that. We multiply, we find what that coefficient is, and we multiply all of those X variables by that coefficient. What we're doing essentially here is we're saying there's a slope between the X variables and the Y variables. And what is that slope? And we'll apply the same slope to every X variable that's present in that sample of the data. And so now we have these Z variables, and we have as many Z variables as Y variables. Now we can ignore that Y variable, where previously we would do a regression from lots of x variables to one y variable. And what we're going to do instead is break this up, and we'll do one regression, a simple single variable regression between each pair of x variables and z variables. And we all the way through our time series from beginning to end. And then what we get, instead of those two charts on the top, which are the same charts that we looked at previously of one variable plotted against the server's CPU time, when we break these things out into these little, much smaller, simpler problems, lots and lots of them, but they're small and simple, and we compute these z variables, and then we plot the query time against the z time, we get lots of very linear looking charts like this on the bottom. So this is the same set of queries, but instead of being plotted against total CPU time, we're plotting it against the CPU time that we blamed on it by computing that slope and those z variables. And we get a very strong linear relationship. So what was a hairball with kind of some vague linearity becomes really strong, really clear slopes through a set of points. And we do this for all of those variables, and here's the results that we get. And here's how we, particularly how we assess the quality of those results. So I want to show you something here before I continue. I'm going to show you how we assess the quality of results in our user interface. And the question is, given one of these columns, such as CPU time and InnoDB reads and lock weights, how trustworthy is the little blue bar that we've put in that column? For example, in query number 5 here, which I've selected and has the dark background, we're saying that this query can be blamed for an accumulated 5.45 seconds of CPU time. How trustworthy is that? And the standard statistical metrics for this are usually not very easy for most people to interpret unless you're trained in statistics. But what we've done is we've created scatter plots just like the ones that I've shown you in that slide. And you can switch from the details to the scatter plots in the right-hand column, and you can look and see whether there's a strong relationship between the metric of query time in this case and the metric that we're splitting apart in this case. Each of these columns gets its own little scatter plot. So we have one scatter plot for CPU time, which looks pretty clean and linear to me. We have one for for InnoDB reads, which looks, it's still got a fairly linear trend there. It's got some outlying points, but I would still trust that a reasonable amount. And then we have lock weights, which is basically a hairball, and doesn't look like it has a very strong linear trend at all. So basically the answer here is trust the CPU time and the InnoDB reads time there, but don't trust the lock weights. And part of the reason for that is that we have different dimensionalities. So that CPU time is tightly related to the total time, partly because their dimension is both in time. The relationship between the query time and lock weights is not quite so strong, and part of that is probably because the dimensions of that are different. Now, if we do the count of queries, if we regress the count of queries, so let's order queries by count instead of by total time, and look at one of them, we may get a stronger relationship. And I actually don't know the answer to this, so we're going to find out. And no, the lock weights are still basically a hairball. So don't trust the lock weights again. And it might seem funny to do this, but one of the things that I wanted to do with this whole technique is not just provide you a quantity in the user interface, but let you decide whether to trust that quantity or not. Because there may be any number of different models that might explain what's really going on inside the system. And a single model, such as a linear relationship of fitting a hyperplane through points in n-dimensional space, may or may not match the reality of what's going on. And so the first question to ask is not how big is the quantity, but how good is the result? There are some standard metrics of quality with statistical techniques like regression. And they're generally numeric. So the R-squared value is one such. The standard error and the T-statistic and the F-statistic and the mean absolute percent error and residual plots. And all of those are useful for various purposes. I wanted to use descriptive statistics with visualization, but not show the descriptive statistics as numbers, because numbers are hard to interpret. And there's a couple of ways that I assessed quality as I was developing this algorithm. Went through many iterations of this algorithm and ended up taking away the name cowbell regression, by the way, when the cowbell was no longer needed, all the crazy sort of heuristic things that I was doing. And I applied this set of tests to all of them to try and figure out whether I was getting good results or not. So one of them was to look at the descriptive statistics. I visualized the heck out of everything, because you can look at those statistical metrics like R-squared value and so forth all you want, but you're not going to see outliers in them. You'll only see outliers when you actually plot the points in various ways. I also not only trained the regression on the sets of data, but then I turned right around and applied it back to the set of data and asked, since I know the outcome and I trained you to achieve this outcome, how closely can you, Mr. Regression algorithm, actually achieve this outcome, given the same input? So it's basically a test of how accurately it can predict what it was trained on. And then finally, holding back, chopping the data set into parts and training on a portion of it, and then trying to use the results to predict another portion. And this helps to prevent against overfitting. And overfitting is a real problem in all of these types of approaches. So descriptive statistics, I'm just showing the same two sets of query classes here. Again, there are hundreds in that sample data set. So I created a table of standard descriptive statistics, and the number of samples that go into it. If there's more samples, the results are generally stronger. The R-squared value, in this case 0.98, the closer to 1 that is, the better. 0.98 is something that would make most statisticians wildly happy. The slope and the t-value of the slope, the intercept and the t-value of the intercept. And t-value is the student's t-statistic, and it's a normalized version of the standard error of the slope and the standard error of the intercept. The non-normalized values are very difficult to study. You really need to compare them against the magnitude of the input values to see whether large or small is good or bad. The predictions versus the actual. So we take the actual input points and then we try to predict them. So and then we plot them on a scatter plot. So on the y-axis here, we have the predictions. On the x-axis, we have the inputs. And if we're doing a good job, if we were completely accurate at predicting the inputs as they were given to us, we would have all of these points lying on a perfect line, slope of 1 going through the origin. So you can see that it's not quite that way. The slope of that first line, for example, is a little bit less than 1. R-squared should be 1. If it were perfect, it's a little bit less than 1. And the mean absolute percentage of error there is 5.9%. I still think that's very, very good. In fact, I know that's very, very good. But this is sort of like playing devil's advocate against the algorithm itself and trying to assess how good the results are. And then in another sample, we get what looks like similarly good results according to the mean absolute percent error, 5.9%. But you can see that the R-squared value is a little bit lower, and the slope looks like 1, so that looks like really good. But when you visually inspect this, you can see the same thing, that the R-squared value is looking like the values are not clustered quite as tightly around that line. So that's why both visualization and these descriptive statistics are really important. Residuals are another common way to look at this. Residuals by themselves, though, are very difficult to interpret because you have to think about the magnitude of them relative to the magnitude of the inputs again. So what I like to do is do relative residuals, a percent of error residual, and plot them over time. So in these diagonal scatter plots here, we're removing the time element and we're just plotting the input versus the prediction. In these residual percentages scatter plots, we're retaining the time element, so we can see if there's a particular region of time over which our measurements are being predicted more or less accurately. And in the first sample, for example, you can see about 2/3 of the way through, there's a period where we're over predicting. All of our residuals, or most of our residuals, are above the line, above the 0 line. So it looks like for that portion of time, we're actually over-predicting for some reason. And you'll always find things like this. You'll always find outliers. Real data is always messy and never nice and neat. And then finally, residual histograms to show the density of those values above and below the 0. And you can see basically most of our values are falling within 10%, plus or minus 10% of the correct value. So all of these are different ways of assessing whether we have any funny outlying spikes in one area or another that need to be explained. And believe me, as I went through the iterations of the many, many ways that I tried to do this before settling on the final approach that I've explained to you, these plots showed all kinds of bizarre things that I would have not seen in any other way. So it's very important to do this, or to do analysis like this. You don't have to. I'm not saying everybody has to do exactly what I did, but I think it's really important to visualize things so that you can find bizarre and unexplained results. There was one surprise here. In some cases, our algorithm predicted that queries could run for an amount of time and then consume more than that amount of CPU time. And I thought at first that this was unphysical, but then I realized that there's a couple of reasons that this actually makes sense in our case. One is the way that we're measuring things. We're measuring time to first byte, and some queries, obviously the time to last byte when the query continues to execute is much longer than the time to first byte. And secondly, there are queries that will do background work. So they actually might cause more CPU time than execution time, especially for things like inserts. They might just be put into a buffer and then do a lot of work in the background. There's also a number of gotchas where you can fall into traps. And again, I played lots of sort of devil's advocate games against myself, and the other people who were working on this with me did as well. There are tricky queries like sleep queries, where the execution time is very long, but the CPU time is essentially nil. There are queries that may have no relationship, and there are unmeasured effects, such as the time to last byte. There are wrong measurements. All measurements are wrong by definition. And there are systems that are just so chaotic that it's very difficult to find any patterns in them at all. Even regression relies on finding patterns, essentially trends in the data. And when the systems are that chaotic, you basically won't get meaningful results. And again, coming back to this question, well, why don't you just measure it instead of using regression? The reason is that all of those gotchas and so forth kind of point towards the reasons why we can't measure it, and regression is sometimes a better way to do this. I'm going to switch back to our user interface here again, and I'm going to switch this back to ranking by total time. So we'll rank queries by total time instead of by count. And what you'll notice here in this particular case, where these queries are, in the top few queries by the total time that they're ranked by here on the left are also the top few consumers of CPU and reads and lock weights. So those things are fairly well correlated with each other, but there are lots of cases where that's not actually what happens. You'll find that query number 3 or query number 8 is blamed for a lot of some resource. Let's switch this out. I'm going to just make room and switch off a couple of the columns and switch on the IO operations column. And you'll see the same thing here, that query number 1 is blamed for the majority of the IO operations. And the reason that this is interesting is that historically, and I've even written about this in High Performance MySQL, I had an assumption that if you wanted to reduce resource consumption on a server and free up resources to run more queries and improve performance by kind of reducing the collateral damage of lots of things contending for resources, you would rank things by time and start from the top and work downwards. And actually the intuition for adding these columns into this interface came from a sudden thought that occurred to me. Wait a minute, what if that's not the case? What if the top queries are really not the top resource consumers, and so we're barking up the wrong tree trying to reduce resources by hunting on those top queries first? What if some other query is really the one that we should be trying to look at to reduce resource consumption on the server? And you don't see it in this interface screenshot, but you will here. There are lots of cases where indeed the top queries ranked by the total time, which is that first column, do not correlate strongly with the CPU time or other resource consumption. So we're not stating the obvious here by doing this regression. We're giving people a chance to figure out if that's the case or not. I have a question on Twitter. Do you need to perform time shifts or summarize for more than 1 second to capture the delayed effects of queries? That's a great question. The tighter that you look into this data, I'll show you here. We're looking across 3 hours, and we can zoom into this data. So for example, let's zoom into the time range where that lump in that query number 2 occurs. The tighter that you look into this data, the more and more you drill down to the small details. Zoom again. The more you'll find that the data gets really chaotic and noisy. And so it's a great question. Should we be looking across longer time ranges in order to capture, for example, if CPU is caused by a query but doesn't show up until some time later? And as you change the time ranges, you will see these queries and the coefficients that we're blaming on them shift around to some extent. So we can keep zooming in here. And now we're looking at a 2-minute range of time. So this is very fine-grained data now, and I can just go 1 second at a time. And if I'm regressing point against point and taking, I'm not sure if you can see this on YouTube, but there's a little dotted line that goes up through all of these spark lines and identifies the points. And then in the left-hand column, that column of total time, we show what the value is at that point. So this regression basically goes pixel by pixel here and takes the values that are changing in that left-hand column and regresses them against each other. But if a query executes here and its CPU time doesn't show up until a few seconds later, then we'll actually miss it. So in a lot of cases, this does benefit from looking across longer time ranges. So let's zoom out to a longer time range. I hope you can see this on YouTube. And I'll just look at the last 12 hours of data. And now each of those pixels starts to represent a longer time range. So for example, here we have 5:20 and 18 a.m. And if I move a pixel over, it's 5:28. So there's several minutes per point in this chart now. 5:34, delicate trying to move 5:36. So there's like a couple of minutes of data aggregated together in each of those points when you zoom out to a longer time range. So that's a great question, and we do see the results change as we zoom in or out, or select a different subset of the data. So there's not one right answer. Regression isn't giving you a right answer that's an absolute truth. It's giving you the best approximation to the input data that you've given it. Hope that answered the question. I had gone through all of this, agonizing over how do we get rid of negative coefficients and how do I know if there's a strong relationship and so forth and so on, and generating all of these scatter plots. And in the end, a light bulb came on in my head, and that light bulb was, if there's a strong linear relationship that's appropriate to perform regression, then if we take the server's CPU time as measured from the process, the MySQL process, and we take the sum of all of these queries and scatter plot them against each other, if there's a strong linear relationship, then boom, we should see it right there. And indeed, with the exception of a couple of weird outliers, we do see that. So this is a great litmus test as to whether this technique is appropriate or not. It makes sense that if you're going to slice and dice things up and then regress the slices and dices against each other, then you should also be able to add them together and regress the sums against each other. So that concludes the audiovisual portion of our flight today. I hope this has been interesting and relevant for you and has explained a little bit more about how we do things. And this regression technique, by the way, we're refactoring some of that code right now so that we can apply it to lots and lots more places in our application, since it's turned out to be pretty useful in the places that I've shown you. So if you're a user of Vivid Cortex, you can look forward to that showing up in other places as well. There is a white paper where I explain essentially what I've gone through in this presentation today, and hopefully reading that white paper can help to clarify anything that I might have bungled in my explanations today. And there's also sample data and code on GitHub for you to look at. The code is in Go, so you can study exactly what's happening and the variations on regression that we do. And it looks like we don't have any more questions at the moment. So I'll go ahead and conclude this. This recording will be available on YouTube. And we're going to send out an email to everybody who signed up for the webinar with the slides and the video of this presentation for your later enjoyment. Thanks for joining us, everybody, and I hope you enjoyed.